right, this video is your chapter 9 takeaways, and there's actually quite a bit of information in this chapter, so I will try to not make this terribly lengthy. So the biggest and the first topic we talked about in chapter 9 is the idea of VSEPR, which is an acronym. Of course, it stands for valence shell electron pair repulsion. If we had to pick the best or the most important word in that, it would be the R for repulsion. So basically, we say that the governing idea of VSEPR is that electrons repel each other, and they want to be as far apart as possible. So they're going to want to achieve a geometry with the largest possible bond angle. There are two kinds of geometries, of course. We have the electron domain geometry, and that includes both bonds and lone pairs on the central atom. And we know, I'm not going to list them because you have this in other places, but we know that the 5 main electron domain geometries are linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. And then the molecular geometry only accounts for the bonds or the atoms that are, connected to that central atom, but keeping in mind that those lone pairs are still there and they're still taking up space. And of course, the molecular geometries are where you get into things like bent, trigonal pyramid, seesaw, T-shape, all that kind of stuff. So again, your geometry is very important to know. It would be, smart to rewatch the geometry video if you are having trouble visualizing those shapes in space. After VSEPR, we talked about where we can expect to see bond angle deviation. So where do we expect that bond angle might deviate slightly from that 90 degrees or that 120 or that 109.5? And that's when we have a lone pair or like a double bond. So like a really good example is when we look at water. So water is bent. Okay, but it stems from a tetrahedral arrangement, and so we would expect this bond angle to be 109.5 because it stems from the tetrahedral geometry. However, these lone pairs up here take up more space than the bonds do, and so what happens is they push these bonds closer together, making this bond angle just slightly less than 109.5. And actually with water, I think it's about 104, and that's because there are 2 lone pairs. Okay, but the important thing here is for you to know when to expect that deviation with the lone pairs on a central atom or with double bonds. Okay, and again, keep in mind, most of the time the question is, what's the approximate bond angle? Well, it's approximately 109.5, okay, but there is some deviation. All right, after there, we kind of backtracked to the previous chapter, and we talked about what's it mean to be a polar bond. Well, a polar bond is an unequal sharing of electrons caused by electronegativity differences. So we talked about almost all bonds are somewhat polar, right? Your 2 exceptions for your nonpolar bonds are your diatomics and your carbon-hydrogen bonds. Pretty much everything else is somewhat polar, right? So, an example would be something like HCl. Okay, of course, this is a polar bond. Chlorine wants those electrons more, and we would be able to draw that. What we were going to, or call a bond dipole, along that bond, showing that chlorine has the electrons more of the time. So a polar bond is just the individual bond being polar. Then where we connected that with our current discussion is, well, what about the polarity of a whole molecule? And so the polarity of a whole molecule depends on the geometry and the individual bond dipoles. Oop, gonna run out of room. So this is where we had something like, CO2, who's linear, and we asked ourselves, you always have to ask yourself, is the individual CO bond polar? The answer is yes. O is more electronegative. So CO2 has 2 polar bonds, but because those dipoles are equal in size, but completely opposite in direction. They cancel, giving you a nonpolar molecule and what we refer to as no net or no molecular dipole, okay, because there is no dipole for the whole molecule. However, the bonds, in fact, are polar. Then you have something like water, where if drawn correctly, water has a bent shape, okay? Water also definitely has polar bonds, and it has two bond dipoles, but in this case, those dipoles do not cancel, and they combine to form an overall dipole kind of pointing up toward the oxygen. So in this case, water is polar, and it has a net dipole or an overall dipole, okay? And one thing I crammed in, I think it was in a lecture, where we were talking about this phrase, and this will come back later, but it's important, we can include it here. Like dissolves like. And we talked about the fact, so what that means is that polar substances dissolve in other polar things, non-polar substances dissolve in non-polar things, and polar and non-polar substances don't dissolve in each other. So my famous example was like oil and water. We know that oil and water don't mix. Well, we just confirmed that water is polar. And so knowing this like dissolves like, what we then have to know is that oil must be nonpolar because the two don't dissolve in each other. Okay. Another big idea in this chapter is the discussion of why bonds form, okay? And bonds form because energy is released every single time. And this was my Three Little Bears story, right, with the Porge or Goldilocks story, and that if I have a bond, trying to form a bond where the internuclear distance is really small, and so that basically I have two atoms almost on top of each other, there's too much repulsion. And notice your energy is positive, which means that energy would be required, okay, to make this happen. If you have your two atoms that are really, really far apart, there's not enough attraction. And basically, they're behaving as individual atoms, okay, with an energy value of 0, meaning you're not releasing energy, but you're also not requiring energy for them to act like separate atoms, but you're really not getting anything from the situation. And then you have the just right scenario where it's that perfect distance to form that overlap, which then leads us to a bond length. And this is this is where the attraction is greater than the repulsion, right? Keep in mind, there's always still repulsion, right? There's always repulsion between positive protons and other positive protons, electrons and electrons. But at that case, the attraction is just far greater than the repulsion. Then we went into hybrid orbitals, which we could talk for a long time about this idea of mixing and promoting and all of that. But the takeaway was hybrid orbitals form because they give better overlap and then thus a stronger bond. And again, this is where we're going to go back to our shortcut, which says where we look at the electron domains on a molecule. It's either going to be 2, 3, 4 for the AP test, but while we're at it, we'll just include 5 and 6. And then we can discuss the hybridization on that central atom. So 2 electron domains gives you an sp. Remember, the rule is 2 domains, and then you have 2 orbitals, s and p, right? 3 would give you an spp, which is written as sp2. 4 would give you a hybridization involving an s and 3 p's. And then 5 and 6 are your your octet violators, which again, the AP test is not going to ask you about, but it's worth knowing. That for 5, it's sp3d, and for 6, sp3d2. So a perfect example would be, I'll just do something really simple like methane Methane has a tetrahedral geometry. It has 4 electron domains, and so 4 electron domains is going to give me a hybridization on that carbon of sp3, and that's what you would be asked. Okay, then we learned about the difference between sigma and pi bonds. Sigma, which gets this like little O with a curly Q kind of thing, is overlap along the internuclear axis. And so I drew you a picture like that would be like an S and an S, right? Because again, here's the internuclear axis. And as you bring those two together, you get something that looks like this. And that overlap's occurring along that internuclear axis. That's a sigma bond. A pi bond is like perpendicular to the internuclear axis, or I often say above and below. So that would be like a py and a py, because you have overlap above it and below it, but you have no overlap along that internuclear axis. See, there's no overlap right there. So that's a pi bond. Okay, and for relatively speaking, if you're comparing one sigma and one pi, a sigma bond is stronger only because it's more of a direct overlap. But from here, the discussion becomes how we know what bonds are. And we learned that all single bonds are sigma. All double bonds are 1 sigma and 1 pi, and triple bonds are 1 sigma and 2 pi. So you could be given a structure. Let me see if I can find something real quick. It's like something like this. Okay, there we go. And asked to talk about how many sigma and pi bonds. Okay, well, we know all single bonds are sigma, so we have 1, 2, 3 sigma bonds, and we know that in this triple, one of them's a sigma, so we have 4 sigmas, and then the other 2 of that triple bond are pi. So we would have 4 sigma and 2 pi without having to draw any kinds of crazy pictures or anything like that. And then the very last thing we learned was this idea of delocalized pi bonding, which basically just means that the electrons are not associated with only 2 specific atoms. And this is due to resonance. So my example in our notes was benzene, but we talked about the fact that so here's your takeaway. Structures that have resonance have delocalized pi bonding. Structures without resonance have localized bonding. And